Hello everyone, welcome back to A4 Analysis. This is the seventh episode of Study Statistics with me. In our last episode, we talked about sampling and sampling distribution, means how can we take a sample from the entire population, and we talked about different techniques how we can take the sample. But after taking the sample, we want to do some experiments on the sample and make some inference about the entire population. So this is the episode where we will be talking about estimating the population parameters using the sample statistics. So whatever experiments we do on the sample will help us to make some important decision about the entire population. So estimations can be useful when we want to make a rational decision without the complete information. Complete information here means we don't have the data for the entire population. Even in such cases, we have to make important decision or important inference about the entire population. But how do we do that? Let's take few examples. One example can be a credit manager wants to estimate the credit worthiness of customers from a sample of their past payments, or a university head of the department wants to estimate how many students will enroll for statistics next year. Each of these cases, we are trying to infer something about the population from the information taken from a sample. Now let's look at few of the terminologies which we will use. First is point estimate. A point estimate is a single number that can be used to estimate an unknown population parameter. The point estimate is only as good as the representativeness of its sample, of course. If the sample is not good enough, how can we expect whatever we are doing after that to be reliable? So we have to assume if our sample is good enough representation of the population, then only the point estimate will be a good representation of the population parameter. If the sample is not good, then the point estimate will also be bad. So the point estimate could be right or wrong just by itself, but it can be more useful if we are giving an error estimate along with that. Say for example, the department head has estimated that next year there will be 400 students in the statistics. But we don't know, it can be good or bad as an estimation, but if we know the range, like it can be off by 5 or 10 students maybe, in such cases it's a really good estimation. But if it is off by say 100 students, it is not a really good estimation. So it's always good to have the estimation of error along with the point estimate, then only it makes more sense to us. Next is interval estimate or confidence interval. An interval estimate is a range of values used to estimate a population parameter with some confidence. Example, instead of giving a single number, department head estimated the number of students in the next batch will be somewhere between 200 to 300 students. And the confidence intervals can be one-sided or two-sided. So instead of giving just single value like 350 or 400 or whatever, if we go for an interval, if we go for a range, this will be an interval estimate. Now estimator and estimates. An estimator is a sample statistic used to estimate a population parameter. So say for example, we want to estimate population mean, then the sample mean will be the estimator. An estimate is a specific observed value of a statistic. Example will be x bar, or sample mean is the estimator of mu, population mean. Now characteristics of a good estimator. When do we say that the estimator is actually good? First of all, it has to be unbiased, means the frequency and extent in which it takes the upper values above the population mean In the same frequency and extent, it can assume values below the population mean. Not population mean, excuse me, it should be population parameter. So what I am saying is, if the sample statistic is distributed in both sides of the population parameter, because of course different samples will have different values, and it will show you as a distribution across the population parameter. So if you are getting 5 sample statistics above the population parameter, you should get 5 below the population parameter as well. And if the highest difference on one side is, say for example, 5 units, then on the other side also it should be 5 units. Efficiency refers to the size of the standard error of the statistic. Same example what we talked about for, like, head of the department is trying to estimate the number of students. The 400 can be a good estimate only when the error is very small, like 5-10 students, if the number is off by 5 or 10 students. But if the number is off by, say for example, 100 students, the estimate is not at all good. So as low as the standard error is, our estimator is efficient. Consistency, an estimator will be consistent if, with the increase in the size of sample, it becomes very close to the original value of the population parameter. So we are starting with a small sample size, but if we try to increase the sample size, our value should get, the sample statistic or the estimator should become more and more precise, and it should get close to the population parameter. If that is the case, then we can call our estimator consistent. Sufficient or sufficiency, an estimator will be sufficient if no other estimator is required to extract additional information about the population parameter. So if we are trying to estimate one population parameter, and with help of one sample statistic we are able to do that, we don't need any other sample statistic, then that one sample statistic will be sufficient as an estimator. That's what we can say. Now let's look at few of the use cases. First one is estimating population mean using Z statistic. So all of these cases are where we want to estimate something about the population from the same thing of the sample. So if we want to estimate mean of the population, we do have sample mean. If we want to estimate variance of the population, we do have the sample variance, and so on. So the first one is population mean, and there are two use cases. Number one is when the population standard deviation is known. So when the population standard deviation is known, we can use this formula. As you can see here from the central limit theorem, we have this z-score formula, and if we rearrange this algebraically, we will find mu, which is the population mean, is equal to x bar minus z into sigma by root over n. Now if we have all this value, we will be able to find population mean. Now this is for point estimate. What if we want to give a range, like for confidence interval? In such cases, the formula will look something like this, where z-score has positive and negative values, and the mu or population mean will lie between these two values. On the left side it has x bar minus z into sigma by root over n, and on the other side, on the upper limit, it has x bar plus z into sigma by root over n. Now how to calculate this z value, this is already explained in a different video. You can also check that out. And this formula is actually meant for large samples where n is greater than 30. This formula can still be used for small samples where n is less than 30 if the population from which the sample is drawn is normally distributed. So with the assumption that the population is still normally distributed, for small samples also we can use this formula. Next is, there is a correction we can use if we want to make it even more precise. There are few commonly used confidence intervals and z-scores here. Take a look at this. And next use case is estimating population mean using t-statistic, where population standard deviation is unknown. So the formula looks almost same, only difference is instead of t-score, instead of z-score, we will use t-distribution or students t-distribution or t-score. There is a t-table. I have already explained in a different video how to get the t-score, but the formula looks something like this, and from this formula again we can derive the population mean and we can derive a confidence interval formula as well. So the t-statistics is actually very robust to the assumption that the population is normally distributed, meaning that it's relatively insensitive to minor violation of the assumption. And t-distribution curve becomes close to standard normal distribution with increasing value of n. But t-distribution is actually a little bit flatter than the normal distribution, standard normal distribution. When the value of n or the sample size increases, t-distribution looks more and more closer to the standard normal distribution curve. Now for t-distribution we need one more thing. Along with confidence interval, we need the degrees of freedom as well, which is the number of independent observation minus the number of independent parameters estimated. So usually it is degrees of freedom is equals to n minus 1 or the sample size minus 1. This is the sample size and 1 is the number of number of parameters we are estimating. So here the number of parameter is just 1, so this becomes n minus 1. Next is estimating the population proportion. So example of population proportion can be market share, proportion of defective goods out of all goods produced, etc. And z-score formula is used in this context. So z-score formula is something like this: p hat minus p by root over pq by n. Now p hat is the sample probability of some event occurring, and q hat is the probability of that event not occurring. So we can take p hat as the probability of success and q hat as the probability of failure. If there is a hat, that is the probability of success in sample, and q hat will be the probability of failure in sample. Similarly, p is the probability of success in the entire population and q is the probability of failure in the entire population. But since we want to know p and p is there, we want to solve this equation for p, but p is there in both numerator and denominator. We can approximate this formula as below. As you can see here, we have updated the denominator. We have substituted p and q with p hat and q hat, so that we can end up with a formula like this, which is almost similar. So p can have a range between p hat minus z into root over p hat q hat by n to the upper limit of p hat plus z into root over p hat q hat by n. So here also, as you can see, we are using the z-score formula. Next we have estimating the population variance. Some of the examples can be, we would like to have the lowest variance in airplane altimeter readings. For safety purpose, it's not enough just to know that the altimeter gives the correct altitude on average. We also want to ensure that the variance or variation of the reading by different instruments are really very small. So this is a case where we want to estimate the population variance. The relationship of sample variance S square and population variance sigma square is captured by chi-square distribution. So this special character, this letter is known as chi, and this is chi-square, and chi-square distribution is used to estimate population variance from sample variance. And this is the point estimate formula where chi-square is equal to n minus 1 into S square by sigma square. And we also need the degree of freedom, which is n minus 1, or sample size minus 1. Similarly, we can have the confidence interval formula as well. As you can see here, for the lower limit we have chi-square alpha by 2, and for the upper limit we have chi-square 1 minus alpha by 2. Now how do we get these chi-square values? We will talk about it in a different video. For this video we are just gonna brush up on the formulas. This chi-square statistics is not a robust estimator to the assumption that the population is normally distributed, meaning that it's very sensitive to minor violation of this assumption. If the population is not normally distributed, we won't be able to use this chi-square distribution formula. Next, determining the sample size in estimating population parameter, which looks something like this. The sample size is n, will be equal to z into sigma by e whole square. So E is the error, Z is the z-score, of course, corresponding to alpha by 2. Alpha by 2 we will get from the confidence interval. So confidence interval, if it is 90%, then alpha will be 0.1, means 1 minus 0.9 will be 0.1, and alpha by 2 will be 0.05. And from the confidence interval and alpha by 2, we will be able to find the Z value. So that's it about estimating different population parameters from sample statistics. Hope you guys found this video useful. If you did, please make sure to give this video a like and subscribe to my channel. And we will meet again very, very soon. Bye guys.